Okay, in this problem, we are looking for constant time expression with Boolean. Use the code from problem 1 and assume Boolean integer typecasting is available. So create a straight line version of the code, and the code from problem 1 is right here. Okay. So the process is similar to before, except that instead of using arithmetic, we are using Boolean. So okay, so first we assume that we have the following, just like before, not B, sorry, A. Okay. Now, then we are dealing with immediately with just the Boolean. We don't deal with the regular expression, the ordinary, I mean the initial expression. So BA, BB. So false, false, true, true, false, true, false, true. But actually, yeah, it's fine. You can also use 0 and 1, but it's the same thing. No difference. Okay, and J will be equals to what? This will be, just J, J, J. The last is J plus 1. And this is all comes from the original logic right here. Yeah. And then next, we instead of the regular term, the multiplication term, we have a min term because we're dealing with Boolean algebra. So the min term is just basically not BA. If you see a false, that's not BA. Or and not BB. Okay. And then false true, then you have not BA and BB. True false, BA and not BB. And true true will be BA, BB, and BB. So now finally the sub expression. The sub expression will be a multiplication of this and this. However, because this is Boolean, we have to convert it back to integer. So this will be J times integer of this one, not BA and not BB. This will be J times integer of not BA and BB. J times integer of BA and not BB. And finally, this will be sorry, mistake. This will be J plus 1 time integer of BA and BB. The resulting code, right? It will be BA equals to not A, BB not B, and then the expression. So the expression will be just J times integer typecast of not BA and not BB, or not BA and BB, or BA and not BB. Okay, plus J plus 1 times integer of BA and BB. All right, that's it. Now for question 4. Okay, for question 4, this will be constant expression with Boolean logic minimization. So here, you convert the truth table into the kernel map. Okay. So here, you will. There are two variables. So our kernel map looks like this. BA can be 0 or 1 or true or false. Doesn't matter. Okay. So, but we have to draw two of them because this is for when J is unchanged. Okay. So, oh, sorry. When J is updated. When J is updated, this is where we will have value of J. And then the other one is when J remains the same. And here, these are the three cases in which they remain the same. Okay. So in order to find this case right here, so we just like in kernel map minimization, you create find a rectangle that enclose the cell, right, that we need to cover. And then what corresponds to this rectangle? You just basically treat this like a coordinate. So it's just 1 and 1, right? That means, for BA 1, that will be BA. And because BB is 1, then it will be BB. Okay, then. Now, for this one, we have to cover these three cells with rectangles. The rectangles has to be power of 2 in both dimensions, right? They don't need to be the same dimension, but both have to be power of 2. So in this case, this will be our first rectangle. Okay, what corresponds to this rectangle? Now, the value of BA is always 0 for these two cells, so it will be not BA. And the value of BB doesn't matter, right? So, value of BB 0 or 1, they both, regardless of the value, we cover it in this rectangle. So that's it. This is BB. To cover this one, we draw another rectangle as big as possible while still power of 2. So it will be that one. So this one corresponds to what term, right? First of all, BA don't make do not distinguish this one. So 0 or 1, we still cover this cell in this rectangle. So therefore, BA is not a part of this expression, but BB is. These two cells are there always when BB is 0. So that means this is not BB. Okay. All right. So the final thing is just basically just create the sub-expression and then add them together. So the sub-expression for this one will be J times the integer of BA and BB. And the sub-expression for this one is J, sorry, I think I make a mistake. This is J plus 1. Yeah, see, right here. This one is J times integer of not BA and sorry, not N, because this is two different terms. So we use or, not BB. Okay. So these are the two sub-expressions. So the final expression will be just the sum of them. Okay, so it will be j plus 1 times integer of BA and BB plus j times integer of not BA or not BB. Okay, done. So this code will have one addition. I mean this expression. One addition right here. Two multiplications. And how many logical operations? Well, we have an and here, that's one. We have a not, that's two, and then an or. So four logical. So that's the complexity of the code. Let's continue for problem 5. So problem 5, look into code from problem 1, transform the code to constant time expression, but we're relying on hardware support. In this case, a conditional move instruction. For conditional move instruction, it will be pretty straightforward. So the secret will be A, B, and create a new one. So let's say temp. Here, temp will be, uh, basically A. A times B and not. Okay. And then you have to have another variable. So in this case, let's say J1. This is equal to J plus 1. And then finally, the CMOV instruction is invoked. Right. So J will be assigned either the value of J or the value of J1, depending on the value of the logic, in this case temp. That's it.